Liza Jane Tan, and I'm one of the members of Quantum. Quantum is here today to discuss to you the topic about linear programming. And I'm actually tasked to discuss to you the introduction part, the history, and when and who conceptualized it. And also, I'll be discussing to you the properties and assumptions of a linear programming problem and on how to formulate a linear programming problem. Now, to start with, there is actually a lot of words associated with linear programming problem. And you can see in here, there is programming, constraints. This is actually one of the properties of a linear programming problem. There is inequalities, um, solve, objective, I'm sorry, which is either maximizing profit or minimizing cost. And also, you can see in here region, feasible region. So we will be testing the feasible region later under the graphical method of solving the linear programming problem. So when you say linear programming problem, it is actually a mathematical technique that businesses use either to maximize profits or minimize cost. Now, this technique has already been existing for so long already, and this has actual applications to the real world. In an organization, for example, many management decisions involve trying to make the most effective use of their limited resources, such as machinery, labor, money, time, what else? Warehouse spaces, raw materials, things like that are utilized to produce products or services. And this LP can actually help the management in coming up with major decisions for their business. Now, let's take a look at the definition of the linear programming. Again, linear programming or LP is a widely used mathematical modeling technique designed to help managers in planning and decision making relative to resource allocation. Excuse me. It belongs to the broader field of mathematical programming. This type of programming refers to modeling and solving a problem mathematically. Now, LP and the general category of technique called mathematical programming have a little to do with computer programming. However, um, computer programming plays a very important role in the advancement and use of LP. Now we'll be discussing, one of my colleagues later will be discussing about QM on Excel, which is one computer program that is really very valuable in solving linear programming problem, which is too burdensome to solve using just a calculator or by hand. So who conceptualized linear programming problem, and when was that conceptualized? So linear programming problem, just a history overview, was conceptually developed by the outstanding Soviet mathematician E.N. Kolmogorov before World War II. In 1939, a linear programming formulation of a problem that is equivalent to the general linear programming problem was given by the Soviet mathematician and economist Leonid Kantorovich, who also proposed the method for solving it. Now, during 1946 to 1947, George B. Dantzig, a mathematician in the U.S. Air Force, independently developed general linear programming formulation to use for planning problems. In 1947, Dantzig also invented the simplex method that for the first time efficiently tackled the linear programming problem in most cases. He noticed that many problems involving limited resources and more than one demand could be set up in terms of a series of equations and inequalities. Now, what are the properties and assumptions of a linear programming problem? So, linear programming problem must have one objective function, one or more constraints, alternative courses of action. Objective function and constraints are linear with the assumption of proportionality and divisibility, certainty, divisibility, and negative variables. Now, with one objective function, All problems seek to either maximize or minimize quantity, usually profit or cost, and we refer to this property as the objective function of an LP. Now, in the case of a manufacturing company, its major objective may be to maximize profit, or for a trucking company to minimize shipping costs. Now, in any event, this objective must be clearly stated and defined mathematically. Now, the second property that LP problems have in common is the presence of restrictions. And these restrictions, we also call this constraints. This actually limit the degree to which we can pursue our objective. Now, when we say constraints, there's maybe limitations to your resources, like money, on how much money only that you can allocate to, for example, the production of certain products that your company is producing, or time, constraints on time that you may allocate in the production for every product that your company is producing. Now, we are therefore uh, going to maximize or minimize the quantity subject to this constraints or limited resources. Third, that there must be alternative courses of action to choose from. For example, a company produces three different products. So the management may use LP to decide on how to allocate its limited resources, say for instance, machinery, labor, etc., among these products. Does it have to allocate its limited resources to produce one product only, or equal amounts of each product? Now, if there are no alternative courses of action, we don't need LP. Okay, fourth, objective function and constraints are linear, which means that the objective and constraints in LP problems must be expressed in terms of linear equation or inequalities. Now, linear mathematical relationships just mean that all terms used in the objective function and constraints are of the first degree, meaning not squared, not cubed, not raised to the higher power, or appearing more than once. In other words, an equation 2x plus 5y equals 10 is acceptable, while the equation 2x squared plus 5y cubed equals 10 is not a linear equation. Why? Because the variable x is squared and the y is cubed, and the variables appear to be the product of each other. Now, next assumption is certainty. We assume the conditions of certainty exist, that is, the number in the objective function and constraints are known with certainty and do not change during the period being studied. Okay, with divisibility, we make the divisibility assumption that the solutions need not be in whole numbers or integers. Instead, they are divisible and may take any form of fractional values. So is it right to say 0.3 number of shares? Yes, it is, because it only means that there is work in process. But fractional values in some other problems do not make sense at all, especially if the fraction of the product cannot be purchased. Say, for instance, 1/4 of a submarine or 1/2 of an airplane. So, an integer in that case, integer programming problem exists. Finally, is the assumption of non-negative variables. So, we assume that all the answers and variables are non-negative, because it's wrong to say that we produce negative number of chairs. So that's what we call non-negative variables. Okay. Now, how to formulate LP problems? Okay. Formulating a linear problem is to develop a mathematical model to represent the managerial problem. And it actually consists of different steps. First step is to completely understand the managerial problem being faced. Now, how would you do it? You need to read the problem, and if there's a need for you to read it, do it, and then digest the problem, and then summarize the data. Now, if you have completely understood the managerial problem being faced, then you can proceed to identifying the objective and the constraints. And in finding the objective, like I said earlier, we figure out what to maximize or minimize. And for the constraints, constraints are limitations on resources. Like I said, this could be limitations on your money to be allocated on in the production of certain products that your company is producing, or constraints on time. Third is to define the decision variables. Decision variables, these are actually things which quantity we need to determine. And four, use the decision variables to write mathematical expressions for the objective function and the constraints. Now, to make this more understandable, let's take some example from the book, The Flair Furniture Company. And this is actually the data of this problem. The Flair Furniture Company produces inexpensive tables and chairs. The production process for each similar in that both require a certain number of hours of carpentry work and a certain number of labor hours in the painting and varnishing department. Now, each table takes 4 hours of carpentry and 2 hours in the painting and varnishing shop. Each chair requires 3 hours in carpentry and 1 hour in painting and varnishing. During the current production period, 240 hours of carpentry time are available and 100 hours of painting and varnishing time are available. So take note of that. Now, each table sold yields a profit of $70 and each chair produced has a profit of $50. Now, Flair Furniture's problem is to determine the best possible combination of tables and chairs to manufacture in order to reach the maximum profit. Okay. So let's apply the 4 steps that I mentioned a while ago. For step 1, here is the sample of the summary of the Flair Furniture Company. So, the summary of data. So, on this side, there is, I'm actually looking at my cursor. Okay. On this side, you can see the carpentry department, the painting and varnishing department. And here, each table produced takes 4 hours in the carpentry department. And here, each chair produced takes 3 hours in carpentry department. And for the total available hours for this week for the carpentry is 240. And for painting and varnishing, that's 100 available hours for this week. Okay. Second step is to identify the object and the constraints. Now, like I said, the objective, looking for or identifying the objective, is to figure out what to maximize or minimize. And here, obviously, the problem says Flair wants to maximize its profit. Okay, so the objective is to maximize profit. Now, the constraints are, first, the hours of carpentry time used cannot exceed 240 hours per week. And the second, this is actually a constraint on time. Now, the second constraint is the hours of painting and varnishing time used cannot exceed 100 hours per week. Third step is to define the decision variables. Now, these are the quantity of the things we need to determine. Now, we assign variable for a number of tables to be produced per week. You assign T, and C is equal to number of chairs to be produced per week. Now, after identifying the variables, we can now use this to write mathematical expression of the objective function and the constraints. Okay. Now, for the objective function, which is to maximize profit, to maximize profit, it can be written as objective quantity is equal to 70 dollars times number of tables produced, represented by T, plus $50 times number of shares to be produced. That's the objective quantity. That's the mathematical expression of the objective quantity. Now for constraints, for the first constraint, the hours of carpentry time used cannot exceed 240 hours per week. Now, in the case of carpentry department, the total time used is 4 hours per table times number of tables produced, plus 3 hours per chair times number of chairs produced. In other words, the first constraint, carpentry time used must be less than or equal carpentry time available, or the mathematical expression of the first constraint is 4T plus 3C is less than or equal to 240 hours of carpentry time. Now, the second constraint says the hours of painting and varnishing time used cannot exceed 100 hours per week. So in the painting and varnishing department, the total time used is 2 hours per table times, is represented rather, with 2 hours per table times number of tables produced, plus 1 hour per chair times number of chairs produced. So that's the total time used. Now the second constraint is painting, because it says that it cannot exceed 100 hours per week. So painting and varnishing time used must be less than or equal to painting and varnishing time available. Or the second constraint mathematical expression is 2T plus 1C is less than or equal to 100 hours of painting and varnishing time. Now 2T here means that each table produced requires 2 hours of varnishing and painting. Note, both of these constraints represent production capacity restrictions and affect the total profit. For example, Flair cannot produce 50 tables and 10 chairs because it will violate the second constraint. Question, why is it violative? Okay, now given that the number of tables is 50 and chairs is equal to 10, now it is violative to the second constraint because 2 times 50 plus 1 times 10, that will give to 100, that will lead to 100 plus 10, which is equal to 110, less than or equal to 100. Obviously 110 is greater than and not equal to 100, so this is violative. Okay, so third, there is a presence of third constraint because, like I said earlier, there is a non-negativity assumption. So the additional constraint is the non-negativity constraint. The values for T and C must be non-negative because all potential solutions must represent real table and chairs, and this can be written as third constraint, table or number of tables produced is greater than or equal to 0, and number of chairs produced is greater than or equal to 0. Must be greater than or equal to 0. So with that, Flair Furniture Company's complete mathematical problem now may be stated as maximized profit is $70 times T plus $50 times C, subject to constraints. This is the first constraint. 4T plus 3C must be less than or equal to 240. And the second constraint, 2T plus 1C must be less than or equal to 100 for the painting and varnishing. In third constraint, what we call the non-negativity constraint, is written as T or comma C must be greater than, or T and C must be greater than or equal to 0. That's non-negativity constraint. Now, solving the linear programming problem, or solving a linear programming problem, does not actually end here. This is just the formulation of the complete mathematical problem. What will happen next is solving either through graphical method or through QM on Excel, which is a computer program. And graphical method way of solving linear programming problem shall be discussed by Miss Claybell, one of my colleagues. Okay, that's the end of my report. Thank you so much, guys. Have a good day.
I will be presenting the graphical solution to an LP problem. So the graphical method is the easiest way to solve an LP problem. This works only when there are two decision variables in the problem. In the example, the variables are T and C, are the tables and the chairs. But when there are more than two variables, it is not possible to plot the solution on a two-dimensional graph. There are graphical solution methods, the corner point solution method and the isoprofit line solution method. But before that, let us first discuss the graphical representation of constraints. To find the optimal solution to an LP problem, we must first identify a set or region of feasible solutions. The first step in doing so is to plot each of the problem's constraints on a graph. Now we plot the variables. Variable T, or the tables, is plotted as the horizontal axis. The variable C, the chairs, is plotted as the vertical axis. Notation T, C is used to identify the points on the graph. Non-negativity constraints mean T is greater than or equal to 0 and C is greater than or equal to 0. To represent the first constraint graphically, 40 plus 3C less than or equal to 240, we must first graph the equality portion of this, which is 40 plus 3C equals 240. So when flare produces no tables, T equals 0. So let's compute. 4 times 0 plus 3C equals 240. 3C equals 240. C equals 240 divided by 3. So C equals 80. Next is when flare produces no chairs, so C equals 0. So 40 plus 3 times 0 equals 240. 40 equals 240. So T equals 240 divided by 4. So T equals 60. So this is now the graph. So any point that lies on the line 40 plus 3C equals 240 satisfies the constraint. The point 30, 40 lies on the plot and exactly satisfies the constraint. So when we compute, 40 times 30 plus 30 times 40 equals 240 hours. The point 30, 20 lies below the plot and satisfies the constraint. So 4 times 30 plus 3 times 20 equals 180. And it's even lesser than the 240 hours available. The point 70, 40, however, lies above the plot and does not satisfy the constraint because the total is 400 hours. Next, let us identify the solution corresponding to the second constraint, which limits the time available in the painting and varnishing department. The constraint was given as 2t plus 1c less than or equal to 100. As before, we start by graphing the equality portion of this constraint, which is 2t plus 1c equals 100. So when flare produces no tables, so t equals 0. So 2 times 0 plus 1c equals 100. So c equals 100. So when flare produces no chairs, so c equals 0. So 2t plus 1c equals 100. 2t plus 1 times 0 equals 100. So 2t equals 100. So t equals 100 divided by 2. So t equals 50. The next step in finding the optimal solution is to find the set of solution points that satisfies all the constraints simultaneously. Now that each individual constraint has been plotted on a graph, it is time to move on to the next step. We know that to produce a chair or a table, both the carpentry and the painting, varnishing departments must be used. In an LP problem, we need to find that set of solution points that satisfies all of the constraints simultaneously. The shaded region represents the area of solutions that does not exceed either of the two constraints. This is also called area of feasible solutions or feasible region, where all constraints are satisfied. And any point outside the shaded area on the right side would represent an infeasible solution. Considering the hours available and hours used, we can say that it would be feasible to manufacture 30 tables and 20 chairs because under carpentry, hours available is 240 and hours used is 180. Under painting, hours available is 100 and hours used is 80. For the 0.7040 or 70 tables and 40 chairs, it would not be feasible because if they manufacture 70 tables and 40 chairs under carpentry department, they will use 400 hours. But then the available hours is only 240. Under painting, the hours used is 180 and the hours available is only 100. The same with the 0.50 and 5 or 50 tables and 5 chairs. Though it's within the hours available for carpentry because if they manufacture 50 tables and 5 chairs, hours used is 215 and the available is 240. So it's within the available hours. But then, under painting, the hours available is only 100, but if they manufacture 50 tables and 5 chairs, they will use 105 hours. Now we are going to discuss the graphical solution methods, the corner point solution method, and the isoprofit line solution method. Corner point solution method. It involves looking at the profit at every corner point of the feasible region. The mathematical theory behind LP is that the optimal solution will lie at a corner point or extreme point in the feasible region. Under corner point solution method, following are the steps to find the optimal solution. So first is to graph all constraints and find the feasible region. Then find the corner points of the feasible region. Third is to compute the profit or cost at each of the feasible corner points. And fourth is to select the corner point with the best value of the objective function found in step 3. The first step in the corner point method is to graph the constraints and find the feasible region. And the second step is to find the corner points of the feasible region. For the flare furniture, for example, the coordinates of 3 of the corner points are obvious from observing the graph. These are point 1, t equals 0, c equals 0. Point 2, t equals 0, c equals 80. Point 4, t equals 50, and c equals 0. And we need to solve the fourth corner point. Now we're going to solve the fourth corner point. So the fourth corner point is where the two constraint lines intersect, and the coordinates must be found algebraically by solving the two equations simultaneously for two variables. Actually, there are a number of ways to solve equations simultaneously, and any of these may be used. In this example, we will illustrate the elimination method. So to begin, we will select a variable to be eliminated. Given the two constraint equations, 40 plus 3c equals 240 and 2t plus 1c equals 100, we can select to eliminate t. So to eliminate t, we will multiply the second equation by -2. So the second equation will become -40 minus 2c equals -200. So if we add 40 minus 40, so 0. Then 3c minus 2c equals c. And 240 minus 200 equals 40. So c equals 40. Next, we will substitute 40 for c in either of the original equation. If we use the first equation, 40 plus 3 times 40 equals 240. So 40 plus 120 equals 240. So t equals 30. So the fourth corner point is 30-40, or 30 tables and 40 chairs. The third step is to compute the profit or cost at each of the feasible corner points. So for point 1, t equals 0, c equals 0, so the profit is 0. For point 2, t equals 0, c equals 80, the profit is 4,000. For point 4, t equals 50, c equals 0, the profit is 3,500. For point 3, t equals 30, c equals 40, the profit is 4,100. And the final step is to select the corner with the best value, which would be the highest profit in this example. The highest profit is found to be 4,100, which is obtained when 30 tables and 40 chairs are produced. Aside from knowing the optimal solution to linear program, it is also helpful to know whether all of the available resources are being used. The term slack is used for the amount of resource that is not used, for a less than or equal to constraint. So slack is equal to the amount of resource available less the amount of resource used. In the flare furniture example, there were 240 hours of carpentry time available. If the company decided to produce 20 tables and 25 chairs instead of the optimal solution, the amount of carpentry time used is 155. So slack time in carpentry is 240 minus 155 equals 85. Another term that we need to know is surplus. Surplus is used with greater than or equal to constraint to indicate the amount by which right-hand side of a constraint is exceeded. For a greater than or equal to constraint, surplus equals actual amount minus minimum amount. So, suppose there had been a constraint in the example that required the total number of tables and chairs combined to be at least 42 units, and the company decided to produce 20 tables and 25 chairs. The total amount produced would be 45. So, the surplus would be 3, meaning that 3 units more than the minimum were produced. For the optimal solution, 30-40 in the flare furniture problem, if this constraint had been in the problem, the surplus would be 70 minus 42 equals 28. The next method is the isoprofit line solution method, and this will be discussed by Jared.
Hi, this is the continuation of topic that was discussed by Ma'am Clay. So this is all about isoprofit line solution method. Once the profit region has been graphed, we need to find the optimal solution from the many possible solutions. The speediest way to do this is to use the profit line method. Starting with a small possible profit value, we graph the objective function. We move the objective function line in the direction of increasing profit while maintaining the slope. The last point it touches in the feasible region is the optimal solution. For flare furniture, choose a profit of $2,100. The objective function is then 2,100 is equals to 70t plus 50c. Solving for the axis-intercepts, we can draw the graph. This is obviously not the best possible solution. Further graphs can be created using a larger profits. The profits we move from the origin while maintaining the slope and staying within the boundaries of the feasible region. The larger the profit will be, the highest profit will be generated when the profit line passes through the point 30, 40. In this lesson, we're gonna focus in linear programming. I'm gonna talk about how to solve it first, and then we can work on some problem. Now, there's two types of equation that we need to be familiar with. The first one is the constraint, and the second one is the objective function. The objective function contains three variables, typically, or more, and the constraint usually contains two variables. The objective of the problem is identified and converted into a suitable objective function. The objective function represents the aim or goal of the system, which has to be determined from the problem. Generally, the objective in most cases will be either to maximize resource profits or to minimize the cost or time. Now let's work on a word problem. A company receives in sales $20 in book and $18 per calculator. The cost per unit to manufacture each book and calculator are $5 and $4 respectively. The monthly cost must not exceed to $27,000 per month. If the manufacturing equipment used by the company takes 5 minutes to produce a book and 15 minutes to produce a calculator, how many books and calculators should the company make to maximize profit? Determine the maximum profit the company earns in a 30-day period. What I'm going to do is to make a table so I can organize all the information that's presented in this problem. First is the sales, next thing is the cost, and last is the time. The time it takes to manufacture the items. There are two items, the books and the calculators. And I'm gonna use B for the books and C for the calculators. A company receives in sales of $20 in book and 18 per calculators. The cost per unit to manufacture each book is $5 and $4 for calculators. And it takes 5 minutes to produce a book and 15 minutes to produce a calculator. And our goal is to maximize the profit or basically maximize the sales. We need to write two constraints and one objective function. So let's start with the problem function. We need to maximize the profit, therefore, we need to maximize the sales produced by this company. So let's start with the objective function. We need to maximize the profit, therefore, we need to maximize the sales produced by this company. So the company receives 20B or $20 per book, and the sales coming from the calculator is gonna be $18 per calculator and equal to S or the sales. S is the total number of sales. We have three variables in this equation, S, B, and C. This is our objective and we need to maximize the sales. And let's go to constraints. And let's start with the cost. The cost cannot exceed to $27,000 per month. And the cost to make a book is $5 and $4 for calculator. It's gonna be 5B, and the cost to make a calculator, that is 4C, and it has to be less than or equal to 27,000. So that is our first constraint. We need to write our second constraint equation, and it has to do with our time. And these are the time to manufacture these items per minutes, and the time limitation is per month. So how many minutes per month? So let's convert days to minutes, and that's our time constraints. This is our second constraint. It takes 5 minutes to produce a book and 15 minutes to produce a calculator. So this is our second constraint. 5B plus 15C is lesser than or equal to 43,200. This is 43,200 minutes is equivalent to 30 days in 1 month. So now we have already these three equations under the objective and the constraints. So let's focus on making a graph, and we only need the quadrant 1. So I labeled x-axis letter B in x-axis and C for the y-axis. And let's plot these two inequalities. So let's start with our first constraint equation. 5b plus 4c is lesser than or equal to 27,000. So let's replace c with 0. So 5b plus 0 is equal to 27,000. Then b, 27,000 divided by 5. Then b is equals to 5,400. So next to calculate is the value of c. 5b plus 4c is equals to 27,000. So let's replace the value of b with 0. So 0 plus 4c is equals to 27,000. Then 4c, then c is equals to 27,000 divided by 4. Then c is equals to 6,750. Then let's make a graph. So this is b and this is c. Let's move on to our next equation. So 5b plus 15c is equals to 43,200, our second constraint equation. Now let's replace the value of c with 0 and calculate the value of b. So 5b is equals to 43,200 divided by 5. Then b is 8,640. Now let's replace b with 0 and calculate the value of C. Then C is equals to 43,200 divided by 15. Then C is equals to 2,880. And let's make another line. So this is our second line here in this area or this line. We try to maximize the sales so we don't need the corner point in 0, 0. Now the solution is going to be in this region, and we have here the corner points with colored green dots. So that's 4. But we don't need these 0, 0 corner points. So again, we will try to maximize the sales so we don't need the corner point in 0, 0. So in this area, that is the 0, 0. And now there's only one corner point to get, and that is the intersection of two lines in this area. So we need to solve these two systems. Notice that these are both 5b. The best thing to do is to add, so I'm gonna multiply the second equation to negative 1. So negative 5b minus 15c equals negative 43,200. And then let's add these two equations. It will cancel negative 5b plus 5b, so 0. Then negative 15 plus 4 is negative 11c, and then negative 43,000 plus 27,000, that's negative 16,200, and we need to divide both sides with negative 11. C is equals to 1,472.72. C represents the number of calculators, so we need to use a whole number and round it to 1,473. So our C is equal to 1,473. Now let's calculate the number of books. So I'm gonna use the first equation and replace C with 1,473. 5b plus 4 times 1,473 is equals to 27,000. Then 5b plus 5,892 is equals to 27,000. Then 5b is equals to 27,000 minus 5,892. Then 5b is equals to 21,108. Then 5b is equals to 21,108 divided by 5. Then b is equals to 4,221.6. So we cannot round up because it will exceed the inequality. So we need to round down. So I'm gonna say b is 4,221. Then b is 4,221. Then c is equals to 1,473. So now that we have all the points of interest, let's make the table. So we're gonna have B, C, and sales. So the maximum number of books that we can have represents this X intercept, which is 5,400 books with 0 calculators. This intercept tells us that we have no books or 0 for books, but 2,880 calculators. And then finally, this intercept, the point of intersection B is 4,221 for books and 1,473 for calculators. So we don't need the graph anymore. So let's find out which of these values will produce the maximum sales. So let's start the first one using the objective equation. So let's start the first one using the objective equation. S is equals to 20b plus 18c. Substitution. 20 multiplied by the value of b, which is the 5,400, plus 18 multiplied by 0, which is the value of calculator, so equals to 108,000. And let's focus on the second point, and that's S is equals to 20b plus 18c. So substitution. So S is equals to 20 multiplied by 0, which is the value of b, plus 18 multiplied by the value of C, so 2,880, so equals to 51,840. So that is $51,840 per month. And for the last one, B is equal to 4,221 and C is 1,473. Substitution. S is equals to 20 multiplied by 4,221, which is the value of B, plus 18 multiplied by 1,473, which is the value of C. Then S is equals to 110,934. This represents the maximum sales, and to determine the number of books and calculators that the company should make to maximize the profit is 4,221 books and 1,473 calculators in a 30-day period. Now, the profit technically the difference between the sales and the cost. So the sales is 110,934 dollars per month. Then the cost is limited to $27,000 per month. So the profit is $83,934 per month. So that's all for my report. So thank you.
Hi, I'm Glacial S. Booted from Team Quantum. Now I will be discussing a topic under Chapter 7, which is using computer programs in solving LP problems. These computer programs are referring to the Excel VM for Windows and the Excel server. So for this particular topic, in order for us to demonstrate how to solve LP problems using these computer programs, we will be using the sample problem, which is the flare furniture problem. So I just have to review what is asked in the problem and what are the given. So what is asked is the best possible combination of tables and chairs to manufacture in order to reach the maximum profit. So basically, it is asking for the units produced with maximum profit. The best combination of units produced for tables and chairs, particularly with the maximum that arrive to a maximum profit. So also shown in the previous presentation is this table, which shows the given or the variables and coefficients for this problem. For the flare furniture LP problem, we have arrived to this decision variables, the objectives, and the constraints. The decision variables represent the actual decisions that we will make, and it is defined as T and C, which T stands for number of tables produced and C stands for number of chairs produced. The objective, on the other hand, is this is now the LP objective of the flare furniture problem. It is a function, so we have arrived to a function in terms of T and C, which states that maximum profit is equal to 7T plus 50C. Now, we arrive also to two constraints of this problem. One, which is the carpentry constraint that states 4T plus 3C is equal or not less than 240. This means that the hours of carpentry time used cannot exceed 240. The second constraint is the painting and varnishing constraint, which states 2T plus 1C is equal to or not less than 100. It also implies that the hours of painting and varnishing time cannot exceed 100 hours per week. Now that we have already determined our decision variables, the objectives and the constraints for the flare furniture problem. We are now ready to solve this problem using the QM for Windows. So let's now go to the Excel QM window. By the way, I am using the Excel QM version 5.2, which I just downloaded from the internet. So for this version, to begin with, we click this Excel QM tab, and under the alphabetical menu, we look for the linear programming. So we click that, and it will direct us to a spreadsheet initialization table. So this table will allow us to put the title of the problem, even the sheet name, the number of constraints, and the number of variables, and also it will allow you to choose whether the problem objective is to maximize or to minimize. So for the flare furniture problem, we type here flare furniture. So we do the same with the sheet name, flare furniture, and then we also enter the number of constraints. So for this problem, we have 2 constraints, which are the carpentry and the painting constraint, right? So we also have 2 variables. So the variables are T and C. So that's our variable. And the objective is to maximize profit. So we choose maximize. Then if we are done, we just have to click OK. So when the spreadsheet initialization step is finished, a ready spreadsheet is prepared for data input. So there's an instruction here that we have to enter values in the shaded area, then use the Run Excel Solver button. So generally, the Excel QM is just very easy to use, in such that you just have to determine what are the variables, constraints, and the objectives, and then if you're ready, you just have to input those data to the Excel QM, and it will compute the answer. It will come up to an answer. So to begin, here we have to change the variable name, which is here is X and 2. For flare furniture problem, this is T and C. T stands for table, C stands for chairs. So what are the constraints? So in our flare furniture problem, we have first the carpentry, second is painting, and varnishing. So that's our constraint. Just have to change that and relate it to our problem. The next step is we input the data here in the shaded portion. So the given here for the objective is we have here for the objective our objective is to maximize profit, so the function is 70 plus 50C. So we put the 70 here, then 50. For the constraint carpentry, we have 40 plus 3C, so we simply put 4 here, and here is 3. So, and what is here in the RHS, the right hand side constraint? It's 240. It should not be less than 240. Under the painting and varnishing constraint, we have 2t plus 2t plus 1c. We have 2 and 1, and under the right hand side constraint, we have 100. Now, we are ready with our data. We are done with our data input. We can now solve the problem by just clicking this one, Run Excel Solver. And when we click this one, the QM is automatically computed. Here we see the results. These are the answer: 30 and 40 and the 4,100. What are the 30 and 40? The 30 is the number of tables produced and 40 is the number of chairs produced. So this is as what is being asked in the problem. These are the best combination of variables to reach the maximum profit of 4,100. So once the problem has been solved, so we have the answer 30, 40 and 4,100. A graph may be displayed by clicking here. So if you ought to see a graph of this problem, just click the graph and it will show us the graph. So here's the graph. The graph shows here our functions, and it will also show us the corner points for C and corner points for T, which is 50 and 60, 100 and 80. Now that we are done computing the flare furniture problem using the Excel QM for Windows, we now proceed with computing the same problem using the Excel solver. So let's go to my Excel window. Let's open our Excel window. So basically the Excel QM for Windows versus Excel solver. The Excel QM is more simplified than using the Excel solver. Why? Because in the Excel solver, you must prepare first the spreadsheet, this one. You have to input the data and the formula given in the problem before you can use the solver command. So it is important that when inputting your variables and your constraint, you have to have one column for each variable and one row for each constraint. So for the flare furniture problem, so this is our title, the flare furniture problem. We first put the variables. Our first variable title, so we put one column for each variable. We have here the T for tables. The second variable would be C for chairs. Now the variable names should be just above the cells for the solution. So meaning we put here the units produced, which will be our decision variables produce later on. Units produced. So it must be above the variable name, our decision variables here, and then the coefficients in the objective function. So any constraint should be in the same columns as this name. So we put here the objective function. And in these columns, later on, we will input the given coefficients for the objective functions, or in the problem are the profits. And then here we put the objective, which is the profit. Our objective is to maximize profit, right? So we just simply put it there. And now we're done with our variables. We input the constraints. So our first constraint is carpentry. Second is painting and varnishing. So we will be highlighting the cells where we will be entering the coefficients later on. So here the profit coefficients, or the objective function coefficients, we will be highlighting it with yellow, and the coefficients for constraint carpentry and painting will also be changing that to yellow. So in line with the profit, below the profit, we will put here the LHS, the left hand side coefficient, which here is the hours used. And then the right side of that, we put here the equality portion of the constraint. So it's not necessarily put, but for presentation, we just put here less than symbol, and we have it centered. And then on the right side of the symbol, we have the RHS, the right hand side coefficient. So in the problem, we will highlight this. We have this given coefficient. Now that we have already determined our decision variables, the objectives, and the constraints for the flare furniture problem, we are now ready to solve this problem using the QM for Windows. So let's now go to the Excel QM window. By the way, I am using the Excel QM version 5.2, which I just downloaded from the internet. So for this version, to begin with, we click this Excel QM tab, and under the alphabetical menu, we look for the linear programming. So we click that, and it will direct us to a spreadsheet initialization table. So this table will allow us to put the title of the problem, even the sheet name, the number of constraints, and the number of variables, and also it will allow you to choose whether the problem objective is to maximize or to minimize. So for the flare furniture problem, we type here flare furniture. So we do the same with the sheet name, flare furniture. And then we also enter the number of constraints. So for this problem, we have 2 constraints, which are the carpentry and the painting constraint, right? So we also have 2 variables. So the variables are T and C. So that's our variable. And the objective is to maximize profit. So we choose maximize. Then if we are done, we just have to click OK. So when the spreadsheet initialization step is finished, our ready spreadsheet is prepared for data input. So There's an instruction here that we have to enter values in the shaded area, then use the Run Excel Solver button. So generally the Excel QM is just very easy to use, in such that you just have to determine what are the variables, constraints, and the objectives, and then if you're ready, you just have to input those data to the Excel QM and it will compute the answer. It will come up to an answer. So to begin, here we have to change the variable name, which is here is xn2. For Flair furniture problem, this is T and C. T stands for table, C stands for chairs. So what are the constraints? So in our Flair furniture problem, we have first the carpentry, second is painting and varnishing. So that's our constraint. Just have to change that and relate it to our problem. The next step is we input the data here in the shaded portion. So the given here for the objective is we have here for the objective our objective is to maximize profit, so the function is 70 plus 50c. So we put the 7 here, 70 here, then 50. For the constraint carpentry, we have 40 plus 3c, so we simply put 4 here, and here is 3. So, and what is here in the RHS, the right hand side constraint? It's 240. It should not be less than 240. Under the painting and varnishing constraint, we have 2t plus 1c. We have 2 and 1, and under the right hand side constraint, we have 100. Now we are ready with our data. We're done with our data input. We can now solve the problem by just clicking this one, Run Excel Solver. And when you click this one, the QM is automatically computed. Here we see the results. These are the answer, 30 and 40, and the 4,100. What are the 30 and 40? The 30 is the number of tables produced, and 40 is the number of chairs produced. So this is as what is being asked in the problem. These are the best combination of variables to reach the maximum profit of 4,100. So once the problem has been solved, so we have the answer 30, 40, and 4,100. A graph may be displayed by clicking here. So if you ought to see a graph of this problem, just click the graph and it will show us the graph. So here's the graph. The graph shows here our functions, and it will also show us the corner points for C and corner points for T, which is 50 and 60, 180. Now that we are done computing the Flair furniture problem using the Excel QM for Windows, We now proceed with computing the same problem using the Excel solver. So let's go to my Excel window. Let's open our Excel window. So basically the Excel QM for Windows versus Excel solver. The Excel QM is more simplified than using the Excel solver. Why? Because the Excel solver, you must prepare first the spreadsheet, this one. You have to input the data and the formula given in the problem before you can use the solver command. So it is important that when inputting your variables and your constraint, you have to have one column for each variable and one row for each constraint. So for the flare for nature problem, so this is our title, the flare for nature problem. We first put the variables. Our first variable title, so we put one column for each variable. We have here the T for tables. The second variable would be C for chairs. Now the variable names should be just above the cells for the solution. So meaning we put here the units produced, which will be our decision variables produce later on. Units produced. So it must be above the variable name, our decision variables here, and then the coefficients in the objective function. So any constraint should be in the same columns as this name. So we put here the objective function. And in these columns, later on, we will input the given coefficients for the objective functions, or in the problem are the profits. And then here we put the objective, which is the profit. Our objective is to maximize profit, right? So we just simply put it there. And now we're done with our variables. We input the constraints. So our first constraint is carpentry. Second is painting and varnishing. So we will be highlighting the cells where we will be entering the coefficients later on. So here the profit coefficients, or the objective function coefficients, we will be highlighting it with yellow, and the coefficients for constraint carpentry and painting will also be changing that to yellow. So in line with the profit, below the profit, we will put here the LHS, the left hand side coefficient, which here is the hours use. And then the right side of that, we put here the quality portion of the constraint. So it's not necessarily put, but For presentation, we just put here less than symbol, and we have it centered. And then on the right side of the symbol, we have the RHS, the right hand side coefficient. So in the problem, we will highlight this. We have this given coefficient. The next step is to write a formula to calculate the value of the objective function. So the formula is units produced for tables times the profit plus the units produced for chairs times the objective function. So that's the formula for computing the objective function. But in Excel, we have here a more simpler function to use, which is the sum product function. So just simply do it like this and then enter. The before this one, the decision variable, just have to fix that one, and we can simply use the symbol $sign. Click here, use E and 4. This is to make sure that when the address of the variables are absolute, this one, and when you copy this formula to another cell, it should not be changed. Okay, so this is now our formula, and since a similar formula will be used for the LHS constraints, we just have to copy this one, the formula, and then paste it here. Now we already have the formula for LHS and the formula for the painting and varnishing constraint. The next step would be, we will be inputting the coefficients now. So the objective function coefficients are the profits of the problem. So for table, we have 70. Profit is 70. For the chairs, we have 50. And the carpentry coefficients are 4, spherical, and 3. And then painting and varnishing, we have 2 and 1. And here, the right hand side coefficient for carpentry, we have 240 and 100 for painting and varnishing. So now we are ready with the problem is now ready for the use of solver. However, if the optimal solution is not found, this spreadsheet has benefits. So what's the benefit? You can either enter different values here to see how the resource utilization and profit change. So for example, what you do is you can do a trial and error to get a profit, a maximum profit. So for example, we put a value of 2 tables produced and 2 chairs produced. We can see that the profit has changed to 240, and the LHS has changed to 14 and 16. So basically, if we will not be using the solver, we can just make a trial and error here, put some values until we reach to an LHS of 240 and 100, since the condition for this problem is the carpentry hours should not exceed 240 hours per week, and the painting and varnishing should not exceed 100 hours per week. So that's it. So we'll delete this one, and then so the data and the data and the formulas are ready. solver command can be used. To begin using the solver, go to the data tab and then look for the solver. So here's the solver. You click the solver, then parameters of dialog box will be shown. So the following input should be entered. Here in the set objectives, we enter the cell address for the total profit. So what's the total profit here? It's a cell D5. So we just click D5. And then we click back. And then by changing variable cells, so what are these? We enter the cell addresses for the variable values. So the changing values. So what's the changing values here? Here, the units produced. These are the variable values address. So back, and then we click here maximize because our objective is to maximize the profit. Under the subject to the constraints, so we just simply click add. We click add, then we enter the address for the LHS of the constraint. What's the address of the LHS? So it's here. So this may be entered one at a time or altogether if these LHS are of the same type. So what are the type? The symbol, this one. So this could be less than or greater than. So since in this problem it's the same, we can just enter it altogether. So like that, then we choose the drop down list, we choose less than or equal, then the constraint coefficient or the RHS, so we choose the address. Since it's still the same, we enter it together like that, then go back. Then if you have or if you want to add another coefficients, you can, and those coefficients with different symbols here, but in the problem we only have two with same symbols, so we click OK. And then we check this one, make unconstrained variables non-negative. Why? Because the T and C should be greater than or equal to 0. So that's the condition in the problem. Then in the select a solving method, we select simplex LP. So once these are done, the inputs are done, we just have to click solve. Solve. And then it will direct us to solver result. So we just want to keep the solver solution, or if you need some reports like answer, sensitivity, or limits report, you just have to click that one, click the sensitivity report, the limits report, and it will give you these reports in a different sheets. So since we're okay, we just have to click OK, and then the solver now gives us the answer here, the 30, the same results we had when we used the QM Excel. So we'll color it blue, and the profit is 4,100. Now that we have already determined our decision variables, the objectives, and the constraints for the flare furniture problem, we are now ready to solve this problem using the QM for Windows. So let's now go to the Excel QM window. By the way, I am using the XLQM version 5.2, which I just downloaded from the internet. So for this version, to begin with, we click this XLQM tab, and under the alphabetical menu, we look for the linear programming. So we click that, and it will direct us to a spreadsheet initialization table. So this table will allow us to put the title of the problem, even the sheet name, the number of constraints, and the number of variables, and also it will allow you to choose whether the problem objective is to maximize or to minimize. So for the flare furniture problem, we type here flare furniture. So we do the same with the sheet name, flare furniture. And then we also enter the number of constraints. So for this problem, we have 2 constraints, which are the carpentry and the painting constraint, right? So we also have 2 variables. So the variables are T and C. So that's our variable. And the objective is to maximize profit. So we choose maximize. Then if we are done, we just have to click OK. So when the spreadsheet initialization step is finished, our ready spreadsheet is prepared for data input. So there's an instruction here that we have to enter values in the shaded area, then use the Run Excel Solver button. So generally, the XLQM is just very easy to use, in such that you just have to determine what are the variables, constraints, and the objectives, and then if you're ready, you just have to input those data to the XLQM, and it will compute the answer. It will come up to an answer. So to begin, here we have to change the variable name, which is here is xn2. For flare furniture problem, this is T and C. T stands for table, C stands for chairs. So what are the constraints? So in our flare furniture problem, we have first the carpentry, second is painting, and varnishing. So that's our constraint. Just have to change that and relate it to our problem. The next step is we input the data here in the shaded portion. So the given here for the objective is we have here for the objective, our objective is to maximize profit. So the function is 70 plus 50c. So we put the 70 here, then 50. For the constraint carpentry, we have 40 plus 3c. So we simply put 4 here, and here is 3. So, and what is here in the RHS, the right hand side constraint? It's 240. It should not be less than 240. Under the painting and varnishing constraint, we have 2t plus 1c. We have 2 and 1, and under the right hand side constraint, we have 100. Now we are ready with our data, are done with our data input, we can now solve the problem by just clicking this one, Run Excel Solver. And when we click this one, the QM is automatically computed. Here we see the results. These are the answer, 30 and 40 and the 4,100. What are the 30 and 40? The 30 is the number of tables produced and 40 is the number of chairs produced. So this is as what is being asked in the problem. These are the best combination of variables to reach the maximum profit of 4,100. So once the problem has been solved, so we have the answer 30, 40, and 4,100. A graph may be displayed by clicking here. So if you ought to see a graph of this problem, just click the graph and it will show us the graph. So here's the graph. The graph shows here our functions, and it will also show us the corner points for C and corner points for T, which is 50 and 60, 180.
Okay, so hi everyone. Today I'll be discussing about my topic, solving minimization problems. Okay, so many linear programming problems involve minimizing an objective, such as cost, instead of maximizing a profit function. Minimization problems can be solved graphically by first setting up the feasible solution region and then using either the corner point method or an isocost line approach to find the values of the decision variables. So basically most of the problems that we will encounter in this chapter is more on minimizing the cost. Okay, so for our example problem, we have the holiday meal turkey ranch. Okay, so I will now read the problem. The holiday meal turkey ranch is considering buying 2 different brands of turkey feed and blending them to provide a good low-cost diet for its turkeys. Each feed contains, in varying proportions, some or all the 3 nutritional ingredients essential for fattening the turkeys. Each pound of brand 1 purchased, for example, contains 5 ounces of ingredient A, 4 ounces of ingredient B, and 0.5 ounces of ingredient C. Each pound of brand 2 contains 10 ounces of ingredient A, 3 ounces of ingredient B, but no ingredient of ingredient C. Okay, so the brand 1 feed costs the ranch 2 cents a pound, while the brand 2 feed costs 3 cents a pound. The owner of the ranch would like to use linear programming to determine the lowest cost diet that meets the minimum monthly intake requirements for each nutritional ingredient. Okay, so first we let x1 be the number of pounds of brand 1 feed purchased and x2 the number of pounds of brand 2 feed purchased. Okay, so our main objective here is to minimize the cost. For this problem, it would be to minimize the cost in cents.